Okay, so in the last video we talked about different models of the atom, starting with Thomson's plum pudding model and leading up to the Geiger-Marson experiment, which was overseen by Rutherford. And then Rutherford used the results of those experiments that Geiger and Marson did, the gold foil experiment, to basically come up with his own model. And Rutherford's model was said to be the first nuclear model. Now remember, the term nuclear just means having to do with the nucleus. And so when we talk about, nuclear weapons or nuclear fission or nuclear fusion, anytime you hear the word nuclear, that means having to do with the nucleus, just like atomic means having to do with the atom. And a lot of people use this interchangeably, but they're not the same thing. So Rutherford's model is the first nuclear model. And remember, we talked in the last video about how he figured out the existence of the nucleus, that small, positively charged, dense center of the atom, based off of the results of the Geiger-Marson experiment. And so I don't want to go over that. Again, some of it is listed on the screen, but we talked about that in the last video. Now, there is a video I want you to see that goes over the Geiger-Marson experiment again, and I'm going to put a link to the video, so I want you to watch that. In this video, we're going to talk more about the nucleus. Now, a lot of people have seen this model of the atom, and this is kind of like the Rutherford model of the atom. You've got the nucleus in the center, you have electrons orbiting the nucleus along the outside. Now, basically, remember that the nucleus is positively charged and the electrons are negatively charged. So we talked about circular motion before. And so in Rutherford's mind, these electrons are kind of like planets orbiting the sun. In the case of the planets going around the sun, we've talked about how circular motion requires centripetal force. And in the case of planets orbiting the sun, that centripetal force is provided by the gravitational force. Now in this case, the centripetal force would be provided by the electrical force between the positive electrons the positive nucleus and the negative electrons, because opposite forces attract. And so Rutherford's model does contain the nucleus. It has a lot of issues with it. It's definitely not correct, but it was a step in the correct direction. And so we talked about that in the last video. Before we start today, I want you to take a look at an IB question from a past exam. I want you to read this question. Try to answer this question. When you're doing IB questions, because we will see more IB questions as we go throughout the next 2 units, when you're entering an IB question, there's a few things you want to look for. Number one, they have what's called command terms that basically tell you how you should address the question. These are words like outline or solve or explain or define that tell you exactly what they're looking for. And so this is the question right here. I'm going to put it in bold and I will read it to you. It says, outline how the evidence supplied by the Geiger-Marson experiment supports the nuclear model of the atom. That is word for word what the IB question was from this topic during, I don't know what year this question is from. It's an older question, but it's still relevant. And also tells you how many marks the question is worth. Okay, so 4 marks, that is a lot of marks for one question. Just to give you an idea, on paper 2, the free response, one of the big free response sections on the IB physics exam, you only have 50 marks overall, and you only need probably about, 15 to 16 to pass. And so 4 marks for one question is quite a lot. Use the number of marks to determine the level of response you have to give, because typically each mark corresponds to a different part of your response. And so you want to think about how to break this down into its different marks. Outline means give a brief account or summary, and a lot of the time you can just bullet point that. Okay, so I want you to pause here, see if you can answer this question. Outline how the evidence supplied by the Geiger-Marson experiment supports the nuclear model of the atom. And as you try to answer this question, keep in mind the number of points, and keep in mind that you answer the question fully. Okay, make sure you address any lingering what or why questions that could be left after your answer. For example, and I'm giving you a hint here, if you are outlining how the evidence supplied by the Geiger-Marson experiment supports the nuclear model of the atom, you probably need to talk about what was the Geiger-Marson experiment, what were the results, and what does that mean, nuclear model of the atom. Okay, so make sure that your answer fully addresses the question. Okay, so pause it here, see if you can enter the question, and in a second I will show you what the mark scheme said from that year on the IB exam. Okay, so here is the answer to the question. At least this is the bullet points that the IB was looking for. Okay, they were looking for these things. Notice, by the way, there's 5 bullet points, and so any 4 of these 5 would have given you full credit. The first bullet point says most undeflected / pass straight through. Now, obviously that is not a complete response, but that's basically just to tell the grader, the person grading this question, what to look for. Okay, so your answer had to say something about the fact that most of the alpha particles went straight through the gold foil. Okay, therefore, this is the second bullet point, most of the atom is empty space. We talked about that in the last video. A few were deflected. Now it says few deflected. Keep in mind, 99.9% of the alpha particles went through the gold foil without being deflected. Okay, so the vast majority were not deflected. Okay, so a very few were deflected, which indicates a small, dense nucleus that was positively charged. Again, there's 5 bullet points here. Any 4 of these 5 would have given you full credit. Okay, and again, this is not to show you what your answer should look like, just that your answer should contain these elements. Okay, so hopefully you got at least most of those. Now let's go on and talk about what is inside the nucleus. Okay, so the nucleus is the positively dense center of the atom, and just to give you some background information, a particle inside the nucleus is called a nucleon. Okay, so a nucleon is, like I said, as the name suggests, it's a particle inside the nucleus. Now, there's 2 types of nucleons that we now know about. At the time that Rutherford came up with his model of the atom, he did not know about either of these. All he knew was that the nucleus was positively charged. He didn't know about protons. He found out a couple of years later. He didn't know about neutrons. That wasn't discovered until, like, I don't know, 15, 20 years later. But we now know that there's 2 types of nucleons. Okay, you have protons and you have neutrons. Protons have a positive charge. In fact, the proton has the same amount of charge as the electron, but it's positive instead of negative. That does not mean the proton and electron are the same with just opposite signs. Proton is way, way, way more massive than the electron. So is the neutron. Just to give you an idea, the mass of the proton and the mass of the neutron, let's say the mass of the proton is very close to being equal to the mass of the neutron. I'm not going to give you those values right now, but they are much, much greater than the mass of the electron. And if you want to know what that means, what does that mean, much greater? I'm talking about thousands and thousands and thousands of times bigger than the mass of the electron. Okay, so protons have a positive charge, electrons have a negative charge, but besides one being positive and one being negative, they have vastly different differences besides just the charge. Okay, so keep that in mind. The nucleus has been found to be much, much smaller than the atom itself. What does that mean, much, much smaller? Well, just to give you an idea, the size difference is something on the order of 10 to the 5, which if you don't know what 10 to the 5 is, 10 to the 5 is 100,000. Okay, now what that means is the nucleus is somewhere on the order of magnitude of 100,000 times smaller than the atom. Okay, now remember, atom comes from indivisible. That's where it gets its name from. Thousands of years ago, we thought the atom was the smallest possible piece of matter in existence, and we now know that there's something smaller than the atom, which is already very, very small, and that is the nucleus that can be 100,000 times smaller than the atom itself. The vast majority of the mass of the atom is concentrated inside the nucleus. By the way, this 100,000 term, of course, that's not a hard number. That's just an order of magnitude estimate. Just to give you an idea what that means, when you watch in a few minutes this video I have here at the bottom, they'll give some analogies, and one of the analogies they give is that if you imagine an atom as being the size of a football stadium, the size of the nucleus at the center of the atom would be like a marble. So if you imagine like a marble at the center of a giant football stadium, that's the size difference, that's the ratio of size difference between the atom and the nucleus. So you'll definitely watch that video. Here, I'll put the link up so that you watch it. But let's talk more about the nucleus. Okay, so I'm going to erase this. And I want to get a little more technical now. So we talked about what a nucleon is. We know what the nucleus is. Nuclei is the plural for nucleus. Okay, meaning you can have one nucleus, you can have two or more nuclei. Okay, so when you see that term nuclei, it's just the plural for nucleus. Okay, don't overthink that or anything. Of course, we know that each individual nucleus has particles known as nucleons inside. Now, these are symbols that you need to know. The number of protons inside a nucleus is given by the symbol Z. Okay, this is an uppercase Z. Okay, the number of protons is called the atomic number. Okay, so you've probably heard about atomic number before in chemistry. The atomic number is based off of the number of protons that an atom's nucleus has. That is what defines an element. Okay, so elements are defined by this value. Okay, it has nothing to do with neutrons or electrons. It's only the number of protons. Okay, so the atomic number is the number of protons in a nucleus. We denote that with a capital Z. The total number of nucleons, that is, the total number of protons plus the total number of neutrons, is called the mass number, sometimes called the nucleon number, and we give this a symbol capital A. So when I talk about the mass number, a lot of people think it has to do with mass, and it doesn't really have to do with mass in this context. Okay, so don't get confused. Mass number is not really to measure the mass, it's just to measure the total number of nucleons within a nucleus. And again, we write that as capital A. So if A is the total number of protons plus neutrons, and Z is the total number of protons, the number of neutrons would just be A, the mass number, minus Z, the atomic number. Okay, so take a minute, make sure that makes sense in your brain. What I'm saying is if you have a mass number of 3, that means your protons and neutrons equal 3. And let's say you have one proton. Sorry, let me erase that. So let's say you have a nucleus that has 3 particles inside of it, and one of those is a proton. That would mean the other 2 must be neutrons. Okay, and so these are some symbols we need to be aware of. In a second, we're going to talk about what's called nuclear notation, which is very, very important for you to know. It's very simple to understand, but it's also something we're going to be talking about like constantly moving forward, so you definitely need to understand nuclear notation. Please pause it here if you need to write any of this down. Okay, so let's talk about nuclear notation and how this works. Okay, now there's lots of different types of atoms in the universe. Okay, so first, how do you name them? Well, here is an example of naming different types of atoms. Hydrogen 1, helium 4, calcium 20, calcium 40. All right, those are all different atoms that exist in the universe. Now, here's how we express those. Okay, this is the general form of how we express those. What you do is, in the middle, you write the chemical symbol. Okay, I'm just going to call that X. In the top left corner, you write the mass number. In the bottom left-hand corner, you write the atomic number, Z. So, for example, what does that mean, hydrogen 1? Like, if I tell you, oh, I'm using hydrogen 1 for fusion, what does that mean? How would you write that in nuclear notation? Well, the chemical symbol for hydrogen is a capital H. Hopefully you know that. What does that 1 mean? The number that comes after the hyphen is always the mass number. Okay, so hydrogen 1 means that I would put a 1 up top. Now, how do I know what Z is? Well, I would just use a periodic table for that, honestly. And normally during this part of the unit, I would give you access to a periodic table because I don't expect you to know off the top of your head different atomic numbers. So what you would do is you would say, okay, hydrogen, what is the atomic number of hydrogen? Oh, it's 1. So hydrogen 1 I would write like this. Okay, H1, 1, meaning hydrogen with one nucleon and 1 proton. In other words, the nucleon in hydrogen 1 is a proton. So hydrogen 1 has 1 proton, and 0 neutrons. Okay, what if I had hydrogen 2? Okay, what is hydrogen 2? We'll talk about that later. But hydrogen 2 I would write like this. Remember, the number that comes out after the hyphen is always the mass number. So it would be H2. Now, hydrogen only has one proton. Okay, that's what defines hydrogen. Okay, so the atomic number is still 1. So what's the difference between hydrogen 1 and hydrogen 2? Well, they both have one proton, but hydrogen 2 has one proton and one neutron. Just like hydrogen 3 would be written like that in nuclear notation. Okay, so when we talk about saying something verbally, helium-4, that's how you would say that particular nuclide in words. How would you write helium-4 in nuclear notation? Well, He for helium. The 4 is the mass number that goes in the top left. And then from a periodic table, I would see that helium has an atomic number of 2. So helium-4 has a mass number of 4, an atomic number of 2. That means there's 2 neutrons in helium-4, 2 protons and 2 neutrons. So this is how you write different types of atoms in nuclear notation. Okay, so I'm going to erase that, pause it there if you need to. And we're just going to do a few more examples. However, before we do any more examples, we need to know how to write the proton, neutron, and electron in nuclear notation. This is very important. Okay, so make sure you get this down. The proton in nuclear notation looks like this. Lowercase p for proton, and then 1, 1. The neutron in nuclear notation, 1, 0, lowercase n. Okay, the reason is because, remember, a neutron has a mass number of 1 because it is a nucleon, but it has an atomic number of 0 because, a neutron is not a proton. Okay, so proton, neutron, and then the electron, again in nuclear notation, is a lowercase e for electron, 0 because the electron is not a nucleon, and so it has a mass number of 0, and then -1 down in the bottom left. And the negative is just because the electron has a negative charge. Okay, so make sure you understand how to write the proton, neutron, and electron in nuclear notation. We're just going to do a few more examples and we'll be done with this video. By the way, just something else to add, it is common both in chemistry and physics to also write the charge of the particle in the top right-hand corner. I didn't do that in any of my examples, but if you do see that, don't be surprised by that. So just, for example, you could have helium-4 that has a charge of +2, and the charge may or may not be written in the top right-hand corner. It's not something we typically worry too much about in physics. It's bigger issue in chemistry just because in chemistry you care more about what's happening with the electrons, whereas in physics, in the unit we're doing now, we care more about the protons and the neutrons rather than the electrons. Okay, but just something to look out for. So pause it there if you need to add that to your notes. And then we'll just do a few quick examples and we will be done. So let's look at some examples. Okay, I think we saw all of these before. This is just showing different isotopes of hydrogen written in nuclear notation. Alright, so pause it there if you need to look at that. Now, I used a word a second ago, and I guess I should have talked about this first. I used the word isotopes, and so you might be wondering, what is an isotope? So please pause it here if you need to. Add this to your notes. You have probably heard the term isotope before, and if you haven't, definitely make sure you take good notes here. So there's lots of different atoms in the universe, and even though you have different elements, you can have two atoms that are the same element that are not the same atom. And the reason is they might have the same number of protons, but they also might have different numbers of neutrons. So isotopes are elements that have the same number of protons, but different number of neutrons. And this is, again, what's called isotopes. So let me give you an example. Carbon 11, carbon 12. By definition, if you look at a periodic table, carbon has an atomic number of 6. Okay, if it did not have an atomic number of 6, it wouldn't be carbon by definition. Okay, so carbon 11 and carbon 12, you would start off writing the same. Carbon 11 has a mass number of 11. Carbon 12 has a mass number of 12. Carbon 14 has a mass number of 14, but they all have 6 protons, which means that carbon 11 has 5 neutrons, carbon 12 has 6 neutrons, and carbon 14 has 8 neutrons. Now, what's the difference? Well, again, same number of protons, different number of neutrons. Why does it matter? Well, because different isotopes of elements have different physical properties, and this is just a very basic example. Okay, carbon 12 is one of the most stable atoms there is. Okay, in fact, if you remember when we defined the mole in the last unit, the definition of the mole is based off of carbon 12. Okay, carbon 14 is not stable. Carbon 14, we'll see later, is what's called radioactive. It is a radioactive atom. If you've ever heard of carbon dating relies on carbon 14. Okay, and so just because you've got two types of carbon doesn't mean that those two atoms are going to behave the same way. One of them is heavier than the other. One may or may not be radioactive. Isotopes are not always radioactive. For example, carbon 11 and carbon 12 are both stable, but carbon 14 is not. We'll talk in the next video about what affects that stability. But again, isotopes are important because they're the same elements, so they behave the same chemically, but they have different physical properties like different masses, different levels of nuclear stability, etc. Okay, so that is what is meant by isotopes, and I think we will probably go ahead and stop the video there before it gets too long. Make sure you add all of this to your notes. In the next video, we'll do a few examples, finishing up with nuclear notation, before we talk about nuclear stability. Now, I said in the last video there's 3 models of the atom: the Thomson's plum pudding model, Rutherford's model of the atom. There's one more, that's the Bohr model of the atom. We will talk about that later after we talk about nuclear stability. Okay, so I haven't forgotten about that third model of the atom. That is something that we'll talk about later. So please let me know if you have any questions. I know some of this terminology might be new, some of it might not be new. But if you have any questions, please definitely send me an email because this is just the foundation for everything we're going to be talking about for the next couple units. Okay, so make sure you understand how nuclear notation works, and make sure you know how to say these things in words. Okay, I will give you a periodic table on any assignments where I think that you need one. So for example, uranium-235, I would not expect you to know that uranium has an atomic number of 92. I would expect you to know that the 235 represents the mass number of that isotope. Okay, so again, we'll talk about that later. Please let me know if you have any questions.